G'day and welcome to this short video on windAroundBuildings in simFlow. In this video I will show you how to set up the windAroundBuildings OpenFOAM case. For something different, we're going to set this up using simFlow. What is simFlow? simFlow is a CFD software for Windows and Linux. Download now a free license. Now the limitation you will find quite quickly is the free version only allows 100,000 cells. Other than that, it's pretty good, worth a look, and this is how you use it. So let's get started. First of all, this is not a tutorial on installing and getting used to using simFlow. For best results watching this video and getting something useful out of it, I'd suggest that you would need to install software and get the hang of it, and then come to this video to replicate an OpenFOAM case. So what we'll do is set up the windAroundBuildings case in simFlow. So what is the windAroundBuildings? Well, OpenFOAM example file uses simFlow. It's got some turbulence, and it looks at the effect of a few sort of building shape geometries and sort of a 10 meter per second wind and how the wind moves around those buildings. So it's a nice example file. It uses simFlow. It's got some turbulence, and it's a good one to try to replicate in simFlow. So let's open up the software and get started. I'm going to open a new simFlow file. From the icon on my desktop, I'm just double clicking on that and just waiting a moment while it thinks about what it's thinking about, and then it launches this dialog box. So it's got the case location, and I'm going to type in windAroundBuildings simFlow. So I've done this previously, so I'm just going to give it a new one, a new name. I'm going to call this windAroundBuildings simFlow number 1. So it's going to open up a brand new case, and that's empty at the moment. So quick tour around the simFlow software, geometry, meshing, parameters, and summary. So there's a left-hand vertical menu area, detailed area on the sort of left-hand column, and then we've got a 3D window. We can toggle between model and residuals. This will plot the residuals as the calculation is running. We'll see that later. And within the model, there is a right-hand navigation through a series of icons to do various things, and we'll go through these in more detail in a moment. For now, we'll be navigating with this left-hand menu and adding detail in this left-hand column. So our first step is to get started on the mesh. To replicate the mesh from the windAroundBuildings case, on the simFlow menu, select mesh and sub menu of meshing. Now we have a number of different tabs that we can navigate between: geometry, base, point, controls, and mesh. So the geometry is where we can add simple geometry here in simFlow, or we could import an STL or an OBJ geometry file at this point. Now we're not going to get bogged down in the details of modeling the buildings in this video. We will just do the background setup. So I'm going to do the background mesh, and I'm going to do the boundary conditions, initial conditions, solver setup, etc. But I'm not going to get bogged down setting up the geometry of the buildings. So that means I'm going to skip the geometry tab and go to the base tab. Here, the default initial mesh you can see has it's just a sort of a size 1 cube. And at this point, I'm going to start looking at the OpenFOAM windAroundBuildings case files, and I'm going to replicate those settings here in simFlow. Now, to do that, I'm just going to make a bit of room on my desktop here. Let's go to the windAroundBuildings case file in the GitHub repo. and that's going to be on my left hand side of the screen. On the right hand side of the screen you can still see the simFlow windows. So from this case setup online, I'm just going to scroll down till I see the block mesh dictionary. So here in the block mesh, and I'm just going to replicate this background mesh here. So x min of -20, y min of -50, z min of 0, x max 330, y max 230, and z max 140. Now the divisions correspond to the XLs. So I'm going to have 25 in X, 20 in Y, and 10 in Z. So that should set up the background mesh here in simFlow. Just got to zoom out on that. I can use the fit view icon, and there we have our background mesh set up in simFlow. Before we move to the mesh, let's just have a look at the names and types on the boundaries. So the -x is actually going to be my inlet, and that puts +x as the outlet. Y negative can be my left. Y plus can be the right. Now the -z is the bottom, and +z is the top. Now the inlet is a patch. I want the inlet to be a type of patch, and the outlet to be a patch, but the rest of them I want walls. Well, actually I want symmetry on the left, right, and the top, and on the bottom I want a wall. So that corresponds to the details in the block mesh dictionary, where we have the boundary. The inlet is a type patch, the outlet is a type of patch, and the ground is a wall, which in my case I've called it bottom. So let's rename that actually. Call that ground. So we type the new name in the bottom here, click on the plus, and that should now be selectable from this drop down menu. So cool. So we've got the ground as a wall, and this is a bit of a typo in my opinion in the OpenFOAM case. It's called front and back, but there's actually 3 faces in there, and I've checked the geometry in ParaFoam, and that is actually the front and back and top. So I'm going to write a new name in here: front and back and top, and I'm going to give the y negative, the y plus, and the top that name. And that's all going to be a type of symmetry. So that's nicely set up. I'm just going to give this the full screen, and we're going to move from the base tab across to the point tab. Now this is a keep point. It's used by the snappy hex mesh routine, and wherever it finds this point, it'll keep the mesh within a closed region of the mesh around that point. So I'm just going to make sure that that's inside my base mesh, and that's what the position 111 will do. Now in terms of the controls, I'm not going to dig deeply into these dictionaries here. I'm going to accept the defaults that simFlow give me and just give you a quick tour. So the castellated mesh, the snap layers, I'm leaving in the general, I'm leaving add layers ticked. Now that's despite the fact that in the case setup, if you scroll to the snappy hex mesh dictionary, you'll see add layers is off. That's a little bit inconsistent with the fact that there are some details about the layers further down the dictionary. So here I want to set the relative sizes to be true, which I've done here. I also want the final layer thickness at 0.5, expansion ratio of 0.2, and the minimum thickness 1e to -0.3. Cool, so that's the controls done. I'll just give this the full screen again, and we are ready to mesh that bad boy. Clicking on mesh, and that's a pretty quick and neat way of meshing in my opinion. And you can then interact with that mesh here in the 3D model view. Something you might like to do is to maybe perhaps add a section view. I'll turn that off. I don't really like section views. We can fit the view. In the graphics object list, we can make it transparent with this little triangle symbol there. Couldn't tell you why they chose that as the thing to toggle the surface versus wireframe, but that's the button. You can also turn off that wireframe view and just go to the surface view here. So I'm going to go back to that one, and let's just go back to fit view, and let's just hide that. Alrighty, so that's meshing done. Next we'll move on to the setup. So we'll move on to the setup tab. First of all, we need to select the solver. From the list, I'm just going to find simFlow and click select. Now I want to work my way through this vertical list of menus. First of all, turbulence settings. I want the RANS, which is Reynolds Average Numerical Simulation, and the model is the kappa epsilon. I'm going to leave these parameters at their default values. Next, transport properties. I want my transport model to be Newtonian, that's fine. And from the database, this is pretty nifty, I'm going to select an air gas material. Select that material, close that. Now, discretization. At this point, we're going to have to look carefully through the OpenFOAM case. And I'm looking for the finite volume schemes dictionary. This dictionary gives me the settings that I want to replicate here in simFlow. First of all, the time scheme is going to be steady state. Convection, now we're looking at the div schemes. So for the velocity field, we're looking for a bounded Gauss linear upwind limited. Linear upwind, and it's bounded. For kappa and epsilon, we want the turbulence, which is bounded Gauss limited linear. Limited linear with a limit of 1. It's bounded. Likewise for epsilon. Dunsky. Now gradients. The default should be corrected. Sorry, the surface normal default should be corrected. A limiting scheme. There is one of those. Should be cell limited from memory. Gradient. Here we're looking at grade schemes default. Gauss linear. That's the bad boy right there. Okay. Moving across to the interpolation, we'll leave that on linear. So that's the discretization, and now we need to move to the solution dictionary, and I'm going to need to replicate the FV solution dictionary here in the OpenFOAM case. So the solver for P is the GAMG, and the solver options, I'm just going to give it 10 cells in the coarsest level, and other than that it's fine as it was in the default. Now the U, K, omega and epsilon solver, I want the smooth solver, and the Gauss-Seidel smoother is fine. Tolerance and relative tolerance is fine as defaults as well. So I'm just going to do the kappa and epsilon smooth solver. Dunsky. Simple in orthogonal correctors is actually 0 in the case. Residuals 1e to the negative 4 is fine. I might just make it a little bit smaller so that the case runs for the full 400 time steps that we'll do in a moment. And relaxation 0.3, 0.7, 0.7 and 0.7. That comes from the relaxation factors here in the FE schemes. So it's either 0.3 or 0.7. U should be 0.7. Cool, so that's the solutions done. Operating conditions, this just gives us the pref cell and pref value 0, 0. Cell zones not used here, and now we are ready for setting the boundary conditions. So setting up these boundary conditions will take a few moments, so please bear with me while we go through this in a kind of logical way. From the setup submenu of the boundary conditions, we're now going to go through and set up the boundary conditions for each of the fields, being pressure, velocity, kappa, epsilon, and nut. We're going to replicate what's here in the OpenFOAM case. So starting from the top of the page, let's first of all do the velocity boundary conditions. Now for the front and back and top, we're looking to set boom, 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 boom. Interesting. So the symmetry should be just as it is symmetry, but the ground is a wall, and we need to set a fixed value with a uniform value of 0. So that's it for the ground. The front and back and top is a type of symmetry, so that's fine. We can just leave that as it is. Now the inlet has a fixed value. It's a velocity inlet. It has a fixed value, and we want the wind coming at 10 meters per second in the positive x direction. The outlet is a pressure outlet, and it should be pressure inlet outlet velocity type. So that's good to go as well. So simFlow is doing a pretty good job so far of following through on what settings I've given it in the previous steps to make a logical guesses about what I want in the next steps. So this is going quite nicely. Velocity is boundary condition is set up. Let's set up the epsilon boundary conditions next. First of all, the symmetry is fine as it is, and what about the walls? Let's set an epsilon wall function. So I'm just going to the only type available here in simFlow is the standard wall function with low Reynolds. So I'm going to use the standard wall function for the ground wall. Now for inlet, I want a fixed value, the uniform value of 0.03. The outlet, I want type inlet outlet, the uniform value of 0.03. So that's epsilon. Next we will set up the boundary conditions for K. Front and back symmetry, ground is a wall, standard wall function is fine. Inlet, velocity inlet. No, we want type fixed value with a value of 1.5. The outlet, we want a inlet outlet with a uniform value of 1.5. So that's K taken care of. Next we've got nut. Symmetry, now the ground is going to be standard wall function. My inlet, I want calculated, and the outlet, I also want calculated. So that's fine at the default values. Finally, pressure. Front, back, and top, symmetry, ground should be a wall, and it's got a 0 gradient. Inlet, I want 0 gradient, and outlet, I want a pressure outlet, total pressure, uniform of 0. So that's done. Boundary conditions are complete. Let's have a look at the initial conditions now. It's all going to be zeros basically. In terms of advanced settings, do we want to initialize a potential flow? I say no. We could map a solution, we're not doing that either. So that's all good to go. Now the output control, right interval 10. Do I want to clean all results file? No, I want to keep them all so I can look at them. We could set up some monitors, I'm not going to do that. So that's now ready to run. So now that we're ready to run, let's write the case. Just give this simFlow window the full screen. So we press run the case. Now we want to run calculation, and that's solved quite quickly. That's because my time step was equal to my end time. So I'll just change that end time to 400, write the case, Let's reset the calculation. So write the case again, and let's run that calculation. So we can see the residuals plotting in real time here on the output window, and because we set that residual control nice and small, it's continuing to run through about 200, 300 here. So it's going to get to the 400th time step and then stop. So the calculation's finished now. We see the residuals are relatively stable, and let's have a look at the results. So we move to the post-processing tab, and let's open up ParaView. So ParaView gives us the ability to inspect the results. Going to do a few things here. First of all, I'll just hit apply, and there's our case. At the moment it's plotting pressure. I'd like to plot velocity. I'd like to move to the end time step. Now there's an encouraging result immediately, and that's the magnitude of velocity goes from 0 to 10. So that tells me that the case didn't blow up. If it had of, that velocity might have increased up to some non-physical number like 1 million or 1 billion or a lot. And if that had happened, it indicates some serious error in the setup. So that's encouraging immediately. Let's have a look at the value of the boundary conditions at the initial time step. So moving back to the beginning of the time, we can see the inlet has a velocity of 10, and all the other boundaries are 0. We can also look at P. So P is 0 everywhere, as it was in our initial conditions setup. Let's move back to the velocity, and we'll just get a slice through the domain and have a look at how it varies at the end of the run. So let's just grab a slice. We'll do that along, let's do it along the Y normal. Apply that, hide the plane, color it by velocity. I just want to change the preset here from that cool to warm to the blue to red rainbow. So we can see that along the ground plane, the velocity is 0, and it increases with height and quite quickly reaches its maximum of 10. And that's consistent from the inlet to the outlet, which tells us that the solution has moved all the way through the domain. So that concludes the sort of initial checks that I would do here in ParaFoam to say that the case has been set up with a reasonable sort of accuracy to then move on to the next step, which would probably be to look at importing your geometry. So in this video we have gone through the windAroundBuildings example case that OpenFOAM added in version 2.4. I've introduced you to simFlow, and I've shown you how to set up this windAroundBuildings case using the free version of simFlow. So that's that. Thanks for listening.